Welcome back to Cloud Computing and Big Data. Today we have our lecture 5, Map Reduce as a Computing Paradigm. And the computing paradigm notion is a little bit alluding to the idea of divide and conquer, which is really a paradigm in computer science that stands the test of time. So many of you that know that a little bit, this divide and conquer, we will come back to this in this lecture. We'll also then quickly understand what MapReduce really is. And then if we look a bit more closer, we will also understand that the Apache Hadoop runtime that is fueling an MapReduce implementation and is quite popular actually in the open source realm is also giving you another, we call it sometimes maybe a sort of hidden phase in it. So you would in one respect say, MapReduce is not really just MapReduce. It would be something that we call map sort shuffle group reduce. But we will come to this during our lecture, and many of these lectures already pointed a little bit to the idea of MapReduce and captures the essence really of divide and conquer. But before we dive into the material to this lecture, let us review what we had the last time. So the last time was really a little bit out of sync. If you want, we said like, okay, we had an introduction to cloud computing, and in a normal situation, you would go ahead and say, well, cloud computing is fueled by virtualization, and then giving you data centers, and then coming from data centers quickly to data center offerings, and with this to the, let's say, hyperscalers, for instance, like MS Azure, AWS, and Google Proc, and Google Cloud Services, and so on. But again, you know, we want to give you the assignment very early in the course. Hence, we injected a little bit this HD insight and also the idea of a little bit more practical ideas on machine learning, because it's also one of the elements where you can really make use of big data, how you can leverage tool sets which are very much basically scalable towards big data sets, which is the other, let's say, element of this course. And so what, let's say, a bit complementary to what we have in the high performance computing course. So hence we left the conceptuals a little bit aside when we dived off in lecture 2 towards machine learning, which in one respect is very good because it's an application domain. It really gives us the reasoning why, you know, learning from data, learning from big data is really an important aspect. First, we have some smaller data sets here in the course in the beginning with logistic regression, but in deep learning in lecture 6 and 7, when we think about the more cutting edge algorithms from learning from data, we will also understand that GPUs at scale are really necessary to actually get insights out of deep learning, and with this also insights out of big data. However, looking then to the idea of conceptualize a little bit, because what you know and have already seen is now HD Insight. You have seen Apache Spark clusters are a little bit, you know, scalable, they're fault tolerant, and basically they're multi-user, so we can have, you know, different HD Insight users on a cluster. And that is something that you would experience also in assignment 1, which was now the essence of the last couple of lectures. So lecture 4 then took a little bit, you know, a step backwards, if you want, and wanted to a little bit set the foundation again, what you have seen in HD Insight, how Apache Spark cluster is fueled, is really basically based on the concepts of virtualization. And the traditional view on, let's say, a one-to-one comparison, maybe with your laptop, with your normal desktop computer at home, you would have something like this, physical hardware, and there's no basically work around that. There will be always physical hardware. You know, sometimes people ask, well, when we have the cloud, then we don't need any physical hardware anymore. No. We need still physical hardware, right? So it will be just somewhere, as this nice picture is alluding to here, somewhere in a Google data center, somewhere. That is something always needed. The same as with your laptop when we come back to this picture. The physical hardware, you know, memory, a disk somewhere, etc., CPU, that's always needed. The question is how you make use of that physical infrastructure. And that's a key ingredient when you come to a, let's say, extremely small scale, which would be your laptop, And when you go to the right side here, to the extreme high scale, where you have different physical clusters that we discussed that all perform, I mean, they have really hardware, something like you see here in the graphic. But of course, they have virtual clusters that you can create then, like for instance, with Apache Spark we have done today, and also in the past, thinking about different lectures that we had already. So in one respect, you would say virtualization really enabled all of this. And if you go one step further, the principal idea, if you go back to the really foundations of this, is that you introduce a sort of virtualization layer, could be enabled by a hypervisor, VMM, as we learned last time. It gives you a virtualized way of seeing your resources, but already shared with others. And these others is now a question what others there are. You could have different guest operating systems. One is a Linux, one is a Windows of some kind, and running applications on this fueled by these virtual machines running on a hypervisor, running on a virtual machine manager. There are different providers of this. There are different people that really, develop on this actively in the community. We have seen open source. We have seen cutting edge vendors like VMware. It's a very hot topic, virtualization, although it's something underneath that the users will never see, right? They have a large data center, like you see here from Google, but they have virtualized clusters that will enable us then to think about the bigger scale. And coming from the, again, left side here to really scale to the things you see on the right side with large data centers, different physical clusters. And now you can even say that one of the physical clusters may be even located on a different location. So you would have different, regions where you have these different physical clusters. And you know that already by looking back to Apache Spark, we had HD Insight saying, well, it was all US central. But there could be also one physical cluster being in US central, but another one actually may be located somewhere in the European, kind of union. So in this sense, this enabled us to really think broader and manage this much wiser. And although this shows a perfect picture on the top where you think about, yeah, no, that's all right. We have virtual clusters, physical clusters. The truth is, if you have seen also in the last lecture, is that sometimes these things fail. Hardware is failing, it's overheating, storage has problems, and network interconnectivity is having a problem because some switch fails. So this enables us, for instance, in this graphic, to have really a live migration during the runtime from one hardware to another, using, again, the concepts of virtualization, of basically performing this app transition. And on the other hand, you would also think like we have a much more, efficiency by resource sharing. And you have your different groups that we had also introduced the last time. One is the green group, one is the red group. But essentially, these different groups share the same resources. And they do, this is the sense of flexible resource sharing that you think is fueled by Google data centers, AWS services, HD Insight. But in the end, this interesting Google or whatever cloud they think about is then fueled by our view we had already in earlier lectures. There's real hardware, there's real storage, there are software, network, and services, which are sort of our user view, right? So it looks like there's a beautiful cloud, extends or shrinks as we need, and we pay for it, we submit requests, paid services, we swipe the credit card, and then we get what we need. But the real implementation view is now something which basically lecture 4 carried a little bit with this graphic, right? So it's quite a complex setup if you want to be a cloud provider. It's not at all that straightforward. Hence, you have, of course, obviously costs. And this goes beyond just the physical hardware that you see really here at the bottom, alluding a little bit to these different pillars you see here on the physical clusters. You have a virtualized platform. You have to enable the virtualization of this hardware. And there are different products that we have seen also last time enabling this. And then you really want to have different virtual solutions. You fire up different virtual machines for different virtual solutions on one layer. The solution is loaded. It should be integrated to some different infrastructure managed in different security and different elements of providing the resource provisioning. So how many worker nodes we maybe need, for instance, on a Spark cluster would be essentially think about this virtualized infrastructure. And then when you want to share it with different users of your company, you need different infrastructure services. So coming from this, let's say, 10,000 feet perspective we established already in lecture 1, where I said to you, what is now the key ingredient of cloud services? You see that the real implementation view of this in lecture 4 is really something which is a little bit more complex and also explains why, of course, there needs to be some cost of using the services, because managing all of this so straightforward as we have seen in HD Insight is, of course, also fueled by many people at MS Azure. And this is just one example, right? Of course, you can think about in AWS services, Elastic MapReduce we had, also in the Google Cloud services. They all have the same order of magnitude of work of get this all working. Plus, in combination, the economics of scale, which makes it, so to speak, work of having these big data centers, also with capacity, sharing it then for very many different users at the same time, that you see a little bit then also when you come again to the ideas that we have here. They're different virtual clusters, but shared on the same physical cluster on the top. I can go on and then say, again, virtualization is a key ingredient of cloud computing. So if there would be not virtualization, there have been maybe not even the development of going towards cloud computing in the past. But I leave that a little bit to other lectures on operating systems, on distributed systems that maybe talk a little bit more about virtualization. So for us, it's just, so to speak, a technique that we need, that we use in cloud computing. And you can see that all the major cloud vendors internationally, and even the centers in the academics, like our supercomputing center in Jülich, we take more and more advantage of virtualization as well. So coming a little bit more then, of course, into our lecture, you see from the color, we're breaking again very early in the course to practical topics, again, to give you the assignment too early. Otherwise, we would maybe now conceptually continue to infrastructure as a service, platform as a service, and software as a service, which are sort of the next idea of climbing up the hierarchy, if you want, on the service provisioning on hardware or different building blocks, as I was alluding to in the prologue or introduction to the Lego blocks, to a full established software as a service. So in one respect, again, this is something we learn from students giving us feedback saying we want to have our assignments very early in the course. Please include these topics a bit more earlier. Hence, we will dive now a little bit to the MapReduce computing paradigm. But it's not a big, strange, change of strategy. So firstly, MapReduce is also something very close to Apache Spark. Apache Spark also offers an implementation of MapReduce. Here we talk about the basics, which are, so to speak, more in Apache Hadoop. But you also know and remember, hopefully, the lecture 3 and lecture 3.1, they still have lots of relationship like the Hadoop distributed file system we talk about today. And then we will basically also, the next lectures will again dive off to machine learning techniques. Machine learning is a big field, so deep learning will be the technique, which is a subfield of machine learning driven by big data really in this course. And we have lecture 6 and lecture 7, and there will be several practical lectures on the way that is alluding again to your assignment to make that very early in the course and not at the end, basically. Hence, let's fasten your seatbelt for an interesting lecture of something you would call a computing paradigm. So here's the outline. We will start a little bit in the first part of the lecture on the MapReduce approach. And we will quickly make the idea of thinking, well, the underlying paradigm is divide and conquer. But before we do this, we want to motivate again the idea why we come back to this. So it's called big data analytics, why we want to have, let's say, big quantities of data or large quantities of data analyzed. And then we come to an interesting comparison to high performance computing, right? Because high performance computing is there, it gives you big, large clusters. So why suddenly we potter off in the cloud? Right, and this has something to do with usability, with the complexity, with the increase of reliability, what we will see, fault tolerance, and so on. understanding then after this divide and conquer paradigm a little bit more that MapReduce is essentially not MapReduce. It is map, sort, shuffle, group reduce. It gives you the key benefit, while I would say instead of 2 phases, you should always understand MapReduce in 3 phases. And interestingly enough, this enables us also to make some sort of short reminder of what a student once in our previous lecture was saying. Isn't that related to Lisp, functional programming? And in a way, it's a bit true. We will see that when we think about the key value idea of it, and then of course the extension of all of this on a larger scale of thing there. This key value data structures enables us, of course, to think much more bigger on a bigger scale, and then enabling us also to understand more this sort, shuffle, group idea based on keys, and then in the distributed fashion. So I give some application examples. We will come to this later in the course as well with HBase, maybe another, let's say, Hadoop, or as they would call open source Apache ecosystem service. But we will also have some examples of the Amazon Web Service and the EMR service. The second part of the lecture will be then understanding the larger ecosystem. So as a computing paradigm, MapReduce is really just a small Lego brick that you have to understand, but coming with a Lego brick and its bigger engine of being fault tolerant. That means when it fails, it will be resubmitted, of being data driven, data oriented, of being, basically the map will find its way to the data source. It's not, as we discussed in an earlier lecture, now a big data transfer necessary to ship it to the map task. Instead, we would say the map task is basically finding its way to the data, right? And we had in earlier lectures the idea of, this different ideas how you could think about data processing, right? And with this, avoiding a lot of data transfer, of having smaller tasks. You remember perhaps a little bit what we had the last time on the word count, right? Sometimes these tasks are very small, but if they travel to the data, instead of the data travels now to a big computing engine running smaller tasks, you save a lot of data by just accumulated data processing directly at the source with simple map tasks. And the same is true then with the reduced set task that maybe then, depending on keys or sorting certain information, then enables us to get some summary statistics, getting some summary out of this data. So in one respect, the second part will be really about the bigger ecosystem that takes basically, just the usage of this as a very small Lego brick, and then added lots of conceptions to it. Today, we would call it a larger ecosystem that is really there. And you have seen that already when I was, starting this up in HD Insight. There are many different services that can be created around basically this Apache Hadoop, Apache Spark, all fueled by open source software. But the key benefit of using cloud computing usually for it that the cloud is already configured for it, for all the different services. You need HBase in a certain version. You basically need, Mahout if you want to do machine learning on Hadoop on a different version. So this versioning aspect is very a key thing. And in the cloud providers we have today, this is really nicely provided. We will show you also then, of course, a hint of how this is used today. And I think one of the key ingredients today is Docker, is basically cloud deployment using these container technologies, fueled also, of course, with more, let's say, workload management systems, with more kubelets, Kubernetes. I will just introduce this because we will have later in the course the chance to go much deeper into it. But interesting to see is that all of that works together. And I think that's the first lecture that really captured the essence of this whole ecosystem, right? Also because we will also change the view again. And at the end of the course today in part 2, we will also think why basically OpenStack offers you these opportunities of creating then a MapReduce cluster very much on your own, combining it then maybe with a public cloud, making it a hybrid cloud, and so on and so on. Including this, of course, as an academic lecture, we will see also some limits of MapReduce. I wanted to discuss also in the light of not only high performance computing with lots of interactions between the different computing engines what we don't have in MapReduce, hence the divide and conquer. So that would be very bad, let's say, to do weather prediction or climate simulations, physical simulations at large, what we do in the HPC course much more. The MapReduce is not really very good for this. It has certain limits and others that we also will talk about. Hence, with this, we will follow a lot of lecture elements that we had in the last, and we will basically connect again, maybe by introducing some repetitions. But the idea is also to show you these lectures are interconnected to each other, right? So that's why they're promises from previous lectures, because we cannot put all in 40 minutes. Hence, we every time come back and forth to these different elements of the course. So let us dive a bit into MapReduce. And you would say that there's this bigger scene where MapReduce was put in the category of saying big data analytics versus big data analysis, which also existing. So it's really a tool set to support more the big data analytics scheme. So that is also more to say a larger technology-driven technique on really large quantities of data that has a whole infrastructure to it. Here we really talk about infrastructure. When you heard the word big data analytics, sometimes it's even based on correlation, not only on causality, which is a very important part that you have to think about. But in the end, big data analytics stand as a term of being really a larger part, really scaling, while data analysis is something which you can even do on serial systems. You analyze the data very much in detail, and often it's of course very time consuming, going down a rabbit hole, and maybe you find out it's basically wrong. And often you're also having limits, right? So you don't have the enabling infrastructure that then big data analytics provides. So in one respect, you would say the difference in the words is important to understand. And then you would more smartly would say we should have to do, in our analysis of big data sets and data analysis that is then fueled by big data analytics. Somehow they are still a little bit here and there in contrast to each other, but they really can benefit from each other. So some motivating examples of this: machine learning again and data mining applications that we will have also in lecture 11 are basically those that you see here as an example, but there are very many in the course over all the time. So the idea mostly in particular case of this, what we have now discussed, is like you would have sometimes a nice parallelism, right? So you would say that big data analytics, MapReduce, Apache, Hadoop, this means we have lots of data, and we need this processing very quickly. And you need this and that makes it nice parallelism, independently processed. So you have a parallelism that is, let's say, a little bit independent from each other. Hence, we were alluding to the divide and conquer we were said in the beginning of the course. And we had this a little bit already with the ranking of the websites, which could be iteratively, step by step by step. There were some interactions, but in the end, we just communicate then after each of the step a little bit the ideas of, pointing to this web page and what is the weight you get from this web page. And there are many different examples, the online social networking sites that we will have also later and here in this part of the lectures, but also, of course, then later when we think about Facebook and so on in later part of the lectures. So independent is a very important word here, because that means there's no communication between the tasks. And this brings us again to the idea of thinking big data analytics was fueled by the idea, and this MapReduce basically come alive, because there were already these supercomputers, right, that had very much InfiniBand, had a very good interconnect. That's where you do weather prediction, climate prediction, physical properties. They interconnect between the different nodes, between the different node cards, extremely on a very low latency, all over the application. But however, you would say sometimes the data intensive computing, if you want, to analyze large quantities of data may not be so physical properties driven and don't need this, let's say, low latency message exchanges in each of the different steps. So, and this brought us to a sort of cheaper parallelism perspective on this computing machinery that you need for this. You see that a little bit alluding to these guys here, putting many different of these, we call, boxes together to offer a cheaper parallelism. So hence, we would have compute nodes, which are more maybe like a commodity sort of hardware. So you don't have the cutting edge as we have now today, maybe with NVIDIA Hopper cards and so on. You have the same. You see that already the pictures carries away the message. Everything is like, very homogeneous, organized, while there's lots of heterogeneity in this idea. But this is, of course, alluding us again to the idea of another paradigm we have in computing. So high performance computing, where the network interconnect is a very dominant factor. You will use the interconnect of all the cores of all the GPUs and host CPUs a lot, while in HTC, high throughput computing, you will see that basically the interconnect is not so important, because you would just once dive off to map tasks or to, let's say, the divide step. We will allude to this in a moment. And then, compute on their own a long time, digesting a lot of data, and then basically coming back at some point in time to do the conquer task. And this is all distributed processing, distributed systems giving rise to it. And you see that the network interconnectivity is not that important like in HPC. Another motivating factor, if you want, is, and this talks a little bit against HPC, for that I'm sorry, saying that, of course, I'm behind HPC since 20 years, and I think it has its relevance. But you also have to say that it is a complex technology these days. In many aspects, it's still a research infrastructure, right? So especially if you think about, Jupyter, our exascale, we right now during the course speaks here, we install in Jülich. That is research. So it never has been such a big system in Europe. So we have to understand how that all works. And even beyond that, a user that I basically picture a little bit like this, that want to use HPC, is basically confronted with a lot of things on the low level, I would say, especially if you think about cloud computing. And that makes sense for many applications that want to stay on one system, that want to leverage the interconnect, right? That I was saying here, you see several computing programming algorithm techniques like MPI, message passing interface. We talked about this a little bit in one, and some student was asking what MPI means. Lots of message exchanges explicitly between the different parallel processes, or you leverage shared memory with OpenMP, for example. So there are lots of different programming paradigms. You have the idea of different systems. You see that a little bit here with having, let's say, different types of systems where you have, the memory is not directly accessible. So you sort of go perhaps through a different chipset. That is one step, but it's still a system which basically can access memory. We call that shared memory possibilities, but they also will find distributed memory possibilities where MPI is really needed to basically go from one processor using the memory space through a network interface to reach another processor. So shared memory, or this unified memory access, and non-unified memory is not so important for you to understand, but knowing the architecture of the system in high performance computing is a complex task, and even more viewed these days with different heterogeneous GPU resources. We still will talk about them in lecture 6 and lecture 7 when we leverage them for deep learning. But the key message to take away is HPC enables you with lots of benefits, but you have to pay the price for it to really go on a lower level, right? And the cloud computing course and the cloud topics are usually on a much higher level. They will still leverage lots of these technologies that you see in all the HPC systems today, different GPUs, different memory, and so on. but the parallelism that you employ and the, let's say, scalability of the system is often much more basically streamlined and much more easier to use. Hence, you swipe the credit card where you actually have to pay for all these higher level cloud services as well, like higher level machine learning service like SageMaker or so in the AWS clouds. Hence, here goes the advertisement. If you're interested, of course, a little bit alluding to the ideas of the course, this is related. The HPC course has lots of things to offer, being very complementary to the cloud computing course. But you have to think about when you take the HPC course, you will be on a very much more lower level, really programming in parallel with explicit message exchanges or leveraged shared memory. So this will be not the world of Spark, not the world of Hadoop, where we just communicate on higher level, let's say, messages that are fueled more on a, basically tool set character, I would call. Hence, the idea was in the end of creating this data machinery on MapReduce, really to hide all of that complexity. You can see here one example of the scientific medical doctor maybe being somewhere leveraging MapReduce, but these people don't want to know everything around the low-level systems like there was in HPC at that time, right? So I don't care what GPU, the point is, give me something very fast, solving my system, solving my machine learning. I want to have 1 or 2 clicks and it should be done. And that's where basically then the cloud comes from. So it has different technical properties, being much more easier to use. It has its usability aspect of bringing people to the HPC, to the kind of computing on scale, which really are not interested in computing. It's, so to speak, a data processing machinery on a very higher level. And it should be, simple and stupid, perhaps not too simple, because it still should be powerful, but that's the key origin. And fueled with this was also the idea that if you program, as I was alluding to earlier in earlier courses, you have lots of failures sometimes, overheated resources, hard disk crash, switch fails, whatever. So that's actually one of the origins also of the term bug, right? The bug in computing is basically a real bug that was somewhere in a big computer. Hence, this is always coming, and we assume that by default. And this is something where in the HPC landscape, the people are still programming in a way, very low level, and hence they're not prepared for this. They have to rerun their job. And here, basically then in this course, when you think about computing and MapReduce motivations, the idea was, can we have something more robust? You see here an example of a big system we have in our Uli Supercomputing Center, 2,000 compute nodes. We have lots of these accelerated nodes, and each of these nodes has even 4 NVIDIA V100 cards. Is already an older system. But the key message to take away is large systems always fail, right, over the time. They have overheated stuff. They have racks that cannot be used, a file system that is down. And basically, you have to deal with this failure on a daily basis. And this is, of course, much more true for the hyperscalers, as you see here, the Google data centers, right? So hence, however, as Google, as Amazon, as Microsoft Azure maybe, you also give service level agreements. So you say, well, the computing is still there. I give you 99.9% availability of computing. So the computing will be there. And the same as networking and everything. So hence, you have to go on. And I think that's the point of creating some software stack, which the idea is now behind the MapReduce and so on, that enables you to think about this on a much bigger scale, and also taking several other benefits into account. One of that we already were alluding to, the data locality. At that time, social media started when MapReduce was built. Facebook was being built, accumulating lots of data from users worldwide. Basically, you see growing a data silo bigger and bigger and bigger, and lots of statistics can be done on this, and moving all of this terabytes today, maybe petabytes or even exabytes, to some HPC system would be also inefficient, right? You probably need several physical trucks to fill this data on hard disk to really get the throughput. Doing this all through internet of petabytes of data is not useful. Hence, the idea is a little bit with this big data analytic movement to compute where the data is, right? Hence, data versus, putting essentially the data to compute. No, we want to do the compute to data. And this is true for, let's say, smaller tasks. Maybe, of course, you cannot have everywhere a big supercomputer where the data is. But this was another movement of this, bringing us then to the distributed processing idea, smaller task. And then this was alluding to the development of coming to the Apache Hadoop system, which is not only the MapReduce engine we will talk about, it's also basically a distributed processing capability enabling a distributed file system. So all the element of data, including data replication, fault tolerance in data, what happens, if one node goes down with the data, do I have it somewhere? So this is one key ingredient where Hadoop really was strong. And this, taking all of these aspects into mind with being very simple, reliable, and then in contrast to MPI, really hiding the complexity. And the scalability by design of data replicating a lot in this distributed file system then was really one of the successes for Hadoop, which in one respect is now coming more to Apache Spark from the processing, because Apache Spark was basically very smart of using more the in-memory we discussed already in the last couple of lectures. I don't go back to this because you have seen that in the last couple of lectures, so let's focus a bit more on the Hadoop engine. And this is also easy to understand, although you would say, and originally invented by Google 20 years ago, it still has relevance today. The map task you will see here has a smaller instruction doing some smaller work on data. And this is a key engine that you first have to understand before we go into more elements. And of course, our practical lecture 5.1 gives you some application examples. We then have this group sort shuffling, as I was saying, by keys. And by doing so, as we had with the word count, right, we said like every word could be a key and the occurrence would be the value. So just to do a simple word count, that would be then the grouping by keys, where the reduce task is then short sorting and maybe even grouping by keys all of those keys which are the same word. And hence you quickly come with this engine to a very powerful engine of counting the words distributed of maybe terabytes of data. And this is the element where then also a little bit of the functional programming with keys and values and so on comes in, and the possibility behind that, because there are of course lots of loaded reduce tasks. And then we have the combined output, which means a counting of words all over your big document stores. And this was the, let's say, you would call that the idea of saying providing a very low level architecture for many high level problems. Hence the divide and conquer, go back to the very principles of computer science is a very good idea to show here. You could think that many of these problems we have, or ratings of a movie, that is something what we want to know, that's a problem. Then we break this down of looking at all the users that all analyze the ratings on all the movies. You don't have to interact with this. You look into all of that independently, nicely parallel, as we call. It was all the different workers, you scale. And at the end, you would combine then the recommendation for a user actually based on the similarity of you. We have analyzed all the ratings. And this would be the movie we recommend. Netflix is doing this on a daily basis, as well as Amazon Prime and others. So it's a very, let's say, trivial approach, if you want, how to do this. But of course, you need a kind of paradigm. You need a processing machine that is able to scale to lots of data. And this is what then give rise to the MapReduce paradigm, which is actually not completely new to break down a big problem into smaller pieces. But if you think about the new element was really then this map sort shuffle group. Third phase was introduced by the Hadoop engine to provide you something which we sort of speak inject to give you another, let's say, programming model that is nice, that you focus on the map and reduce using key value pairs. as we were suggesting, for instance, with the map elements, you program the map task, you program the reduce task, but inherently you define a key value structure, and the key value pairs would be then sort, shuffled, grouped based on the framework. So you have this third phase, which is loaded, which gives you lots of, let's say, powerful elements of going through data, which are often the idea of summary statistics of, let's say, the word count. If you go back as an example, right? It's a good idea of saying grouping this by words as a key, and then you don't have to program any of this, right? You have a simple map counting all the words. You have a simple reduce going through all the keys, how many words there really are. And then you have a combined input. The sort shuffling will be taken care of the framework. The distributed processing will be taken care of the framework. Then the handling of big data, of faults in the processing, will be taken care of the framework. So it's an extremely usability friendly way of really going through terabytes, if not petabytes of data. Okay, here the note goes, I'm not funded by IBM, but I think it's an interesting video to understand a little bit more in terms of sandwiches, how basically the MapReduce idea works and how the key value structure, we will talk also a little bit more, of course, in the second part of the lecture, is really fueling a lot of applications if you think about breaking problems down to the key essence. And this is alluding to this kind of structure, providing us with, an idea of going through some data with K1, V1, providing us this list with a new kind of key structure that is there. But then take away the message that, of course, the framework is doing some magic in between of really sorting and shuffling and grouping whatever the task is of this keys to provide us in the list with this kind of different values that you can easily combine in the reduce task then to an final element of the application, like we had in the word count, that we will also look now a little bit as an example, but we had this before. You can see that the key is really a word, and you just count the occurrence. This is a map task computation, really very not intensive. Then you would say the reduce, we basically we go through the word key and the list we had and just, say always +1, +1, +1, +1, another word, another word, another word. And you would say the addition of this is also a very trivial task. Hence, computationally, it needs to be small because it's very close to the data. We don't have a high performance computer directly close to it, maybe still a cluster having and digesting many of this MapReduce tasks. Now, what's happening in between is then this idea of grouping the keys so that this really works with the different reduce operating on this different key tasks. In practical lecture 5.1, we will look at this more intensively. Here's another example, really looking a little bit more maybe into the memory structures. You have the different types of words coming in. You will have a configuration size cutting it, and then you have different map tasks, just counting the occurrence, how many foo's and cars and bars are there in these different lines that you basically have to parallelize, right? This is also what the framework can give you. And then you have this aggregating values by keys, which is then automatically done by the framework. That's where the sort, shuffling, and grouping comes in. The sort of hidden step I was saying, summarizing then all the foo's, all the bars, all the occurrences, And then you have the reduce, which is a simple math operation, again, combining, or if you want, just add all the different values you have to give the final idea. And the point is really this middle step that the framework will give you in terms of automation. If you want to scale this higher, you can now imagine that, we had this in an earlier lecture already. The Jan resource manager is now doing this with very many map tasks here in the word count example, maybe of very different users also, bringing us then quickly to the scale that we had also on the MS Azure Spark cluster, then with different worker nodes distributed in this map reduce and so on. But our assignment 2 and practical lecture 5.1 will also explain you a little bit more about this, how this is distributed and so on. Finally, I would just give some remarks to some applications we will have also in later lectures. Needless to say, some of these ideas are also alluding to some databases designs that then leverage this idea of MapReduce and so on. So we'll talk a little bit here about Facebook using, for instance, NoSQL key value stores in Apache HBase based on Apache Hadoop with 700 terabytes of data. So nothing like your small MP3 collection at home. So this is something where they have to be on scale every single day. And this is just one part, really, of the whole infrastructure of Facebook. But they're leveraging this computing paradigm. And I think here's a video that summarizes a little bit also the difference, or basically the dependencies between Apache Spark and Apache Hadoop that is fueled by the MapReduce engine. And we continue then with the second part of the course after a short break.